Okay, good morning to everybody. Can I ask one of the colleagues that are following us remotely to give us thumbs up whether they can hear us? Okay, thumbs up. Can you please tell us from your microphone that you can hear us as well?
Yes.
Yes, we can hear you, yes.
Excellent.
Yes,
So,
okay.
Yes.
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 Excellent. Thank you very much, ladies and gentlemen. In, I believe, about 12 countries across our continent. Thank you for joining us, all of you, those that are currently here and those that are following us remotely. We're running a bit late, so I'm going to be very, very fast, or we'll try to be very, very fast. We are connected from Politecnico di Bari and more specifically in the Indicatech department. And we're very, very happy to be here for the MedCell Summer School, a school that is organized in 4 modules with a lot of anxiety and a lot of enthusiasm for all the MedCell group that worked a lot to provide you with this event. There are going to be 4 full days, morning sessions and evening sessions, as you saw from the program. Thank you for enrolling. And the greatest thank of all should go to our organizing committee from Poliba. They gave all their good work and a lot of trials and errors and a lot of work with a big group headed by Professoressa Gabriela Balaco. A warm thank you. Gabriela, come here, they need to see you. So, this is Professoressa Gabriela Balaco. And of course, behind Gabriela, there's a big group. Alessandro, Gaetano, Maria Rosaria, and many, many more. Dolores, of course, Fidelibus. Apart from the Italian group, there's a very, very big group from Germany, Cyprus, Greece, and Tunisia that had worked to give you this, and Turkey, sorry, I forgot Turkey, to give you this event. People are still coming, tutors. They're going to meet with us in the next few hours. And we're looking forward to a very, very exciting event, which will run from 9 to 1 in the morning with a break for coffee that is going to be served outside this room at around 10 or 11, depending on how we roll with the lectures. Then we're going to be having a lunch break from 1 to 2 sharp. Please keep the times in order to be able to give you whatever we have planned to give you, to offer you. During lunchtime, our colleagues from the organizing committee of the Politecnico di Bari have already sent you a list, a Google form, where you can declare if you want to order lunch to be delivered here, or if you prefer to get lunch from one of the coffee shops around. Please, guys that are watching remotely, don't be jealous. We're having a wonderful time here. Yesterday, we had a fantastic ice break event. It's a pity we don't have you here, but we're going to have a couple of beers in the coming nights as well. So, in the sessions, from 2 to 5, the practical sessions, the practical exercises. Practical exercises, depending on the tutor's theme of each morning, will vary from Google Forms to hands-on exercises, case studies, or number crunching on cases on Please mute yourselves if you're not using the microphones. Okay. I lost track. Okay, so they're going to be the practical exercises, which is big fun. And the greatest advantage of this summer school, may I say, is not that it's high potential theory, it's state of the art. All right, you're going to hear state of the art, but on top of that, you're going to hear practical case studies that all of us have worked in the past many, many years, and especially focusing on the very, very hard work MedCell project has delivered over the past 2.5 years. So sit comfortably, enjoy, keep your cameras closed to help those that don't have a big bandwidth to attend, and amongst the foremost, keep your microphones off. If you want to intervene and ask a question or you have a problem, there are 3 different ways. On your Teams platform, top on the reactions, click and you'll find a hand. Raise your hand. If this doesn't work, but give us a couple of minutes, we cannot respond immediately. You can open the microphone, say, excuse me, or I need to ask something, and depending on where each lecturer will be, he will let you do it right then or in a few minutes time. And the third option, of course, is use the chat option. On Teams platform, there is a button on top right again, which says chat. If you press chat, you can connect immediately and type in any question you have, press enter, and everybody sees it. Okay? Unless you want to address the message to a specific attendee, therefore you will need to select the person you want to send the message. Can you hear me down there? Is it loud and clear? Excellent. So, Gabriela, of course.
Yeah. Dolores, please.
I said many things to you yesterday night, and I will repeat for those that I met the first time to this moment. And I'm very happy because I like very much young people. And this means that I see that there is an interest in the topics I always liked in my life. And this is a hope in the future. You see that climate change is running, and the effects, especially on groundwater salinization, will be worse and worse. And for us, the project has a sense because we are worrying about the future, and the future is yours. So please think that your future of, I hope, hydrogeologists is important, much more important than in the past, because water is decreasing, because water is in danger. And so this is our contribution.
Excuse me to interrupt. We cannot hear Dolores. It seems it is muted.
I think the mic is closed from your part.
Dolores, your mic is closed. You're muted. We cannot hear you.
Yeah, you're put on mute.
Now it's okay.
Okay.
Now?
Now it's okay.
Now it's okay.
Yes, it's fine.
You have to repeat what you said because we lost the best part.
That I'm happy. So I can say you again that I'm happy. So good luck for you, for your life, and always learn more. Always. So for sure your knowledge, because it's the best you can do for you. Thank you very much for being here.
Thank you very much, Dolores. I see that there are some raised hands. Is it something which is not resolved? Was it the microphone or is it another problem? Vicky Stavropoulou is the first one. Are we okay or a problem is still existing? I see 4 hands up. Okay, if the problems are resolved, please lower your hands.
Yes, it's all okay. Thank you very much.
Okay, so please lower your hands again, reset them. Now, before we get on with it, let me just for a minute remind you that the first thing is that the computer always stacks when you don't want it. Right.
Yes. Director of the department is here.
Okay. So we have the privilege to have the director of the department of Dicatec here. And he is here to address us and welcome all of us, those that are here with us and those that are remotely connected.
Nice to meet you.
And Professor Jules from you.
So,
Sì, sì, sì. The webcam is open.
okay,
Yeah, no,
because of his online presence. So, hope that post-COVID will finish as soon as possible, and we come back all together to meet in reality, not online. So I welcome you at this summer school. I'm very happy you are in our university and department. This year was a very special year for our university. We reached many successes, and also our department, which was included in the better departments. I'm not real photogenic, so sorry. Was included in a short list of the better departments in Italy, so I'm proud for that, and I'm proud to guest you here. I know there is a good professor group, and this is also a satisfaction for me. So I thank Gabriella to organize this school. I guess that the greatest part of you come from the Mediterranean area. So to participate to the competition among the excellent departments, we choose to the research field, which is the resilient in Mediterranean regions, like as coasts and underground water. So you know that we have a big problem with water in these markets, and so welcome to this summer school, which help us to follow on the street that we have already traced for our excellent project. So have a good job, and hope to meet you again in the next days.
Thank you.
Professor, thank you very much. And on behalf of the managers and my institute, would like to present you.
Fine, thanks. Thanks. So you are part of our excellent project.
Yes. Thank you very much.
Professor Jules.
So have a good day.
Thank you.
So after the address by the head of the department of Dicatec, let's quickly go through the tutors that you're going to be hearing from today and who helped organize all this school. We're starting with Professor Christopher Kulz from the Technical University of Lübeck, Professor Marisa Maria Dolores Fidelibus, of course, and Vangelis Ziritis, who is going to be remotely connected. Then the second module of tomorrow is organized by Professor Cüneyt Güler from Turkish Mersin University and Haralabos Dulgeris from the Soil and Water Resources Institute in Greece. Day 3 will be run by Professor Fedon Kyriakidis, who was planning to be here yesterday, but due to COVID, unfortunately, he is stuck in Cyprus. However, we're going to have also Katerina Nikolaidou from CERF in Greece and Konstantinos Panayotou that made it from Cyprus, and he is here with us. Day 4, also Vasilis Pisinaras from my institute and Thodoris Mergidis from CERF in Thessaloniki, Greece are also participating, contributing in Module 3. And last but not least, Day 4 on Thursday is going to be run by Vasilis Pisinaras from Soil Water Resources Institute. Myself, I'm Andreas Panagopoulos from the same institute. And of course, Professoressa Gabriela Balako and Professoressa Padua Hamzawi. This is the program roughly as you saw it. I don't want to spend time with it. Please remember that we run from 9 to 1 and from 2 to 5. The only exception is on Thursday that we need an extra 30 minutes in the end in order for you to help us assess how the whole thing went, if you were satisfied or not, and this will be the time to crucify us. So we're done with this, I think, and I would kindly ask you before we start for the next 5 minutes to get your smartphones on hand, because we're going to start with a nice game for the next 2 or 3 minutes. And of course, everyone is welcome to participate from the tutors. Of course, all of you, please come with your mobile phones on hand. Those that are connected remoted obviously will have to do it. And please connect to the web page either using this code number that you see or scanning the QR code on the right part of the screen. To do it, you have to be connected to the internet, either through Wi-Fi. There's a Wi-Fi connection detailed to get through here on the whiteboard, or you can use your data plan for those of you that are remotely connected. I see many, many hearts, and I like it. Let's hope that you're going to feel the same on Thursday evening. Okay, I take it you are already connected, right? So let's quickly, instead of spending time to present yourselves, let's get together and know each other. First of all, give it a try. Can you connect? We're getting there. Good, good. More and more. Give me some more. 42. Oh, that's nothing. Where are the stakeholders? Stakeholders are here as well. Okay. We're getting there. We're struggling. A bit more. Lovely. And more are to come. So let's go to the hardcore here. Please tell us your first name. It's another way to meet each other. Many different names. Many, many, many. Fantastic. Excellent. We're getting to a very nice canvas here. Right. And more are coming. Good. Interesting. It's getting bigger and bigger. The one that Columbus had. I like this one. Excellent. So, since we know our names now, let's see where do we come from. Which countries do we come from? You can select your original country or the country you are residing on now. Whichever would be good. Okay, excellent. 3 continents so far. And how many countries? Many. Good. Fine. And what are you working on? Are you a student, a professional, a professor? What are you? Let's see, what do we get? All kind of stuff. Excellent. So most of you are students, either PhD or postdocs, some undergrads. Of course, we have some researchers with us. And it goes on, a long list. Excellent. So we are the group that we are expecting to have. And let's see how you feel about being here and about being connected. Please be honest about it. And you can send as many answers as you like, because I suppose there are many feelings that we share each other. Fantastic. Good. Motivation, happiness, gladness, excitement, enthusiasm, luckiness, optimism, all positive stuff. It can only go well with all this. Chris, what do you think?
That's a high bar.
It can only go well. Watch it, guys. We have a very difficult task ahead of us. People are waiting a lot. So, and last but not least, are you ready for it? Let's see here what you feel. And let's test your Italian for those of you that do not come from Italy. I'm sure you can understand. Okay, yeah, hopefully you can understand what she means. I don't see any no's. Good, excellent. So, Chris, our students are ready to start. I think we can start. Thank you all. Have a very nice week here. And those of you that are remotely, you are here. We're all a family here. So enjoy it and get the most out of it. Chris, the floor is yours. And we leave you to the very, very capable hands of Professor Kurs. Chris, they're all yours. Enjoy, guys.
Thank you. Sorry for the small delay. And before I start with the lecture, I want to make some remarks and just introduce myself quickly. So first of all, do you hear me well? Is the technology okay? For those who are listening online also? Seems to be the case. Otherwise, Dimitris, you just give me warnings if there is something in the chat. Yes, I would like to repeat the words of Dolores because those who are not here missed them, and I think they are important. She expressed her hope and optimism because many young people are here whom she likes. And she said that it's about the future of your life, of the environment, and you are responsible for it. And so she is happy to actually pass on the information, the knowledge to the younger generation. And this is what the summer school is about. I just wanted to repeat this. Before we start officially, I would like to thank the University of Bari for hosting us, Gabriela and all the organizers for preparing the meeting. Again, to give us this opportunity to talk about salinization and different methodologies to actually study it. Just a few words about myself. My name is Christoph Kurz. I'm a hydrologist with a PhD in hydrogeology. I worked in the Mediterranean since, I think, 1994. First with projects in Cyprus, in Greece, Israel, and Jordan. And my first education being hydrology. And since I have studied with Christian Leitlenburg, famous tracer hydrologist, I initially started working with tracers, artificial tracers, to study hydrological processes. So this is my big ambition, or was my big ambition, it still is, And then I realized very quickly when I started working in arid environments, in the Mediterranean, semi-arid environments, that artificial traces don't have much because processes are slow. And we need something that is inherent, embedded in the water, information in the water. And so I started studying environmental isotopes, like 1995. Did my PhD in the Namib Desert in Southern Africa, and then worked a lot, and since then on groundwater in the Mediterranean. Today I want to share this knowledge that I had the opportunity to develop with many colleagues on environmental isotopes. I'm now professor at Technical University of Lübeck since 2014. I had the opportunity to work in an isotope laboratory, so I also had first-hand practical experience in projects all over the world, practically. So I will also try to address practical issues of application. Do you hear me well also in the last ranks? Okay, thank you. Yes, so before you start a lecture, especially when it's a long one, it's a good idea to just think about what is this all about? What is the objective today of the course? What do I want, do we want to achieve? And in short words, I would like to share with you an approach that I try to apply, and that is to actually use environmental isotopes to understand, but also to calculate and quantify information about the water cycle. Today, it's especially about groundwater salinization. So often environmental isotopes are used in a qualitative manner. We try to see something. This is good, gives us additional information, but today I want to focus on going a bit further on doing calculations, and we will practice this in the afternoon. So I try to actually convey what I call quantitative or semi-quantitative environmental isotope hydrology. Now I would love to have the METRI tool, but since I don't have it here, I will just ask you, who has previous experience with environmental isotopes? So if you just raise your hands, if you're in the room. Okay, so water, and if you're not in the room, if you attend online, please just share this through the chat, and then Dimitrios will give me a sign. So I will try to actually explain what environmental isotopes are first. I will also explain the basics. And I think I tried this lecture on Dimitrios on Friday, so I try to cover the whole way from start towards quantitative isotope hydrology. So this is the objective. The second objective is learning objective. We want to learn something about salinization processes. So we want to broaden our understanding of how salinization works. And I hope that at the end of this lecture and at the end of this week, you will not only have learned techniques to identify salinization, but that you have also hopefully a broader understanding of how diverse the processes can be that actually lead to salinization of water. So just a remark, if you have any questions, if you don't understand anything, please react immediately. I will probably finish my sentence, but I will try to react immediately to your concern so that I don't lose you. Okay, so there's no problem just saying, hey, I don't know where we go. And before we start, before I explain the structure of the lecture, I want to make a second remark, kind of framework remark. for the entire week, maybe. And this is like to put everything into a big perspective. Hydrological cycle is basically the recycling of water from oceans through the sun. It's a big distillation process. And since we live on continents, like some at the shore, but some others further inland and being landlocked, we depend on moisture that is transported from the oceans into the continents. And of course, this is the basic process of the whole water cycle. I mean, this is evident. Now, when the water flows back to the ocean, I just want to mention this again, because with climate change, the dynamics of evaporation, precipitation over oceans, and the net balance of how much will be transported into continents might change dramatically. And I think this is the worst threat of climate change to us, because all our societies depend on the water flowing back to the oceans. We use it. Now, as the water flows back to the oceans, it actually picks up, because water is an excellent chemical agent for dissolving things. It picks up things, it picks up salts, picks up gases, picks up all kinds of chemical constituents. And it can also become saline. And this, plus the danger that seawater encroaches, is the objective. So I just wanted to create the framework again. So we try to study the process of water becoming more saline, at the end useless for many purposes. And this is not only seawater encroachment, it can also be the excessive dissolution and enrichment of water with salts, for example, through a closed basin process. So an active water cycle will actually be not critical, and a water cycle that slows down, that loses dynamics, that loses connections, hydrological connections, is actually what makes water salty, plus mixing. And this is just an introductory remark, because we will talk about residence times and age of water. And in this context, this framework idea is important. So what is the structure of the lecture? I started with the introduction, and then the second chapter will be principles. I will try to explain how stable isotopes work. I will explain definitions, but also how we do simple calculus using isotopes. I will then talk about residence times and methods to determine the age of water. And I refer to the context that I just made. You can actually measure how active the water cycle is, how dynamic the exchange of water is in an aquifer, and we'll deal with these methods. Then I will talk about compartment modeling. It's an approach that helps us to study water fluxes based on chemistry and isotopes. So the overall objective of the lecture today is that we learn quantitative isotope hydrology, so that we learn not just to see there is evaporation, okay, the water comes from mountains, maybe this is this source, that we learn to actually calculate things. And this is the extension of this idea. And then I will make some final remarks. So this is the program for this morning. And in the afternoon, we will do exercises, but I will try to already introduce some exercises during the morning time, so that we don't have a stretch of 3-4 hours theory without doing anything. This is not very productive. So we'll also try to calculate some things. Can you see everything well? Is that fine? Okay, what are we talking about? For those who want to further study environmental isotopes, I can also refer you to our book, Traces in Hydrology, that I've written with Christian Leitengut and Piotr Maloszewski. The book covers artificial traces, and environmental traces. That was new at the time when we published it, and the methods that you need to analyze tracer signals, artificial and environmental traces, plus many examples and case studies. I can provide a chapter of this book, the chapter that I've written on stable isotopes, and also the chapter 6 or 7 on the technical planning and case studies. So if you want to actually read more and get into more depth, then I can refer you to that. So I will share this afternoon. I will share a web page to which you can access all these this material. And this table is taken from this book. It summarizes this left. It summarizes the isotopes that we have and that we can use to study water, residence time, and also processes, chemical processes that we observe in water. So first of all, we have the environmental isotopes, such as deuterium. So these are the two variants of the hydrogen element, and oxygen isotopes. There's O18. We also have O17 that's now being used more and more because we have new instruments with which you can measure this isotope that we didn't have 20 years ago. We have carbon-13. And then we have nitrogen-15. I will also talk about the nitrogen method, sulfur-34. But we also have gases that you can work with, like helium-3. We have tritium, carbon-14, argon-39, krypton-85. I will talk about krypton-85, but not about argon-39. It's really used quite well. It was developed by Marcus Forster, one of the owners of Hydroisotope, who died early. And it's a very nice method, very useful, but rarely used. Silica-32. So these are all isotopes that are natural, stable or radioactive, and that we use that are introduced by the environment itself. So we don't do anything actively. On the other hand, you also have artificial traces, but we will not talk about them today. If you're interested in artificial traces, I give a course on artificial tracer hydrology at University of Darmstadt every year in March. So then you can come to this course. It's a blog course, or we have this online as well, but this is not the topic today. It's not the topic because all artificial traces need to be actually introduced into the water cycle actively. And you need to be present to monitor them and to analyze the result. Now, this process that we study often take 10, 20, 100, sometimes thousands of years. So we will not be there to analyze our own injection. And this is why this is not a good idea. Especially when you come to lowlands, dry areas, artificial traces don't work anymore. And it takes too long. And by definition, when we study salinization, we are in lowlands, we are at the coast, and the Mediterranean is quite dry in many regions, so often it doesn't work. Sometimes it works in karst areas. We had some examples of very fast salinization processes with karst springs that got reverse flow by over pumping inland. So this is something that you could study with artificial traces, but there are just very, very limited applications. Then we still have, at the very bottom, pollution traces, for example, CFCs, but also SF6. So these are all the chemicals that we produce as industrial societies and post-industrial societies. And often this pollution happens at a global scale, especially SF6 krypton 85. These are gases that our industry produces for several purposes, and that unfortunately have polluted the entire Earth and are still polluting. And we have limited the use of some of them, like CFCs, chlorinated fluorocarbons. But some of these industrial or pollution traces are still polluting the Earth until today, and their concentrations are increasing. And this is not good, since they are very stable. SF6 has residence time in our atmospheres of many hundred years. So radiation, UV radiation actually almost doesn't destroy SF6. It takes a very long time to destroy it. This is why it stays in the atmosphere. It's very climate active. This is why the concentration, it accumulates in the atmosphere. But it has a scientific benefit. And the scientific benefit is that you can use it for age damage. So we can actually read the age of water from the concentration of SF6 in water. And I will show you how this works. And in the both traces in hydrology also have a worked example, complete worked example that we will practice in the afternoon, so that you see how this actually works. Okay, so this is the scope. These are the traces that we have at our disposal. Now, laboratories are changing. In the past, we could only work with mass spectrometers mainly. We're trying to purchase new ones. So these are very expensive devices, €500,000 to buy them, starting like 150 to 200,000. And in the past, you needed physicists, often PhDs, really very well-trained, experienced people to run them and to keep them running. So, and you needed special climatization for these rooms, very high operating cost. This is why you just have few labs. But since a couple of years, we have, since it started in 2000, more or less 2003, with the paper by Castle. So since like the end of 2008, 2009, 2010, we have new devices, laser spectrometers with which we can measure some of these isotopes very rapidly and very easily. So these devices are a bit cheaper, cost 80 to 140,000 euro, and they are a bit easier to operate. So they can be operated by a trained master student, and they give us access to O18 deuterium, C13, N15 measurements at very fast pace. So we can produce values every second, because it's based on laser absorption. And labs become smaller and more easily to operate. You see the, just check whether the pointer works. So you see such a device here. You can operate it with 230 volt. And so it's actually getting a bit easier to do isotope hydrology now. These devices work with a cavity, which is basically a cylinder, most often times to which you apply a vacuum, then inject the gas that you want to measure into the cylinder, and you send a laser beam that is actually being repeated into an endless loop by vibrating mirrors. You measure the absorption. These devices require very high precision of the laser wavelength, and this is why most of these devices is temperature controlled to keep these devices going. So we have two of these devices in our lab. This gives us completely new insights into how isotopes work, and most of the knowledge that we have gained with these devices is the basis of what I will introduce in the theoretical section that comes next. So this is basically how this looks like. So you send a laser beam into the chamber, into the cavity that contains, for example, vapor. And you can imagine the water molecule like a Mickey Mouse head and 2 ears. And this is vibrating all the time because of energy. So the ears are going like this, and the whole thing is shaking. So there are, depending on the degrees of freedom, different movements possible. And the heavy isotopes moves differently. And because of that, it has different absorption wavelength. They are just a tiny bit shifted. And with this device, you can measure these absorption wavelengths basically, and thereby we can measure the concentration of not only H2O, but HHO and DHO. So this is the this is a very special one. So this is a heavy isotope that has two deuterium. It's very rare, very rare to produce it, adulterated. So this has a different absorption wavelength, and we can use this effect to measure the concentration of isotopes. But before we talk about that, I need to explain you what isotopes really are and how they are defined. Isotope means in the same place, same location. I often start with the history of chemistry, in which the discovery of stable isotopes was a disaster. It was bad because chemists used oxygen as a reference mass. And in the beginning of the 20th century, they noticed that oxygen doesn't always have the same weight because the precision of scales was sufficient to actually measure these tiny differences. And this was the problem because water from Norway didn't have the same weight, or oxides from Norway didn't have the same weight as oxides from the Mediterranean or from Africa. So this was discovered, and I call this like a chemist's nightmare. And a reaction to this was that actually many water samples were measured to define differences in weight, molecular weight. And then at the same time, the theory was developed why we have actually different isotopes. So the concept of stable isotopes was developed, and basically oxygen, we all know this, is a mixture of oxygen that has 2 additional neutrons, or 18, and the normal oxygen that has just 8 protons and 8 neutrons. We also have one with 7 neutrons, which is O17. And as a result of this, the molecular mass of these 3 different stable oxygen isotopes is different. You have the same problem for hydrogen. So you have a normal hydrogen, which just consists of a proton, and you have a hydrogen that has a proton and a neutron. They are both stable. And if you add 2 neutrons, it becomes unstable, and you have a radioactive liquid. Now, it took some time between the discovery that masses of oxygen and of hydrogen differ to the point that we could really measure the abundance of these 2 isotopes. So if we look at the ratio, for example, between the heavy isotope O18 and the light isotope O16, it took some time until the near spectrometer was developed, which is a device with which you can actually measure the ratio of the heavy to the light isotope. Basically, you have a big magnet, you create a plasma or a gas with charged particles. You send them along the magnet, it's deflected, and you have cups to actually pick up the separated ions from that beam. And as a result, you always get a value R, which is the ratio between the 2 abundances, Ni and N. So this is the basic definition that we need to work with isotopes. Now we will go through the principles of isotope hydrology, and when you do some theory, it's always important to know where you want to go. Yeah, so we have an objective. Overall objective is to have tools to understand salinization. This is where we want to go. The second objective, as I said, is that we want to use isotopes for this, because we don't have to add them to the water. They are there. They tell us something about these processes. And we want to learn to do it in a quantitative manner. So this is why we do this. Like, just a short feedback question, to whom this is completely familiar? Who knows this stuff? Not the case? I'm still on safe ground? Okay. So this is really important, because if we don't do this, there is a way of doing isotope hydrology like artificial intelligence. You're learning. You read papers, many papers, people doing this. This is how I learned it too. And people apply things and you learn, oh, okay, I need to use this diagram. Oh, I will do that. So you pick up methods. But it doesn't give you the ability to calculate, to do this on your own, to walk on your own legs. So this is why we go back to the basics. Yeah, but it will not be like this for the next 3 hours, don't worry. So this is the isotope ratio for stable isotopes of oxygen. This is the isotope ratio for the stable isotopes of E. I talked with Dimitrios this morning in the taxi, and I told him we should actually use concentrations. And I think it's a point that we should make more often, because you all know how to work with concentration. The concentration of chloride, 500 milligram per liter, you know immediately what this is. This is easy. So you have 500 milligrams of the substance, chloride, in 1 liter of water. Easy. Now, isotope physicists, they invented another notation. Instead of using concentrations, which is familiar to everyone, they work with ratios. And in the beginning, it's a bit difficult to wrap your head around this. Because now, instead of, if we compare this to concentrations, concentration of O18 would be, we take O18 divided by all the oxygens that we have in water. It's O18 and O16. When we deal with water, we compare to the volume. So we will actually compare to all the water. But here, in this notation, we just take the heavy isotopes and we divide by a fraction by the light isotope. This is a different notation. And it creates some difficulties in the beginning, but it's also useful, and it was necessary because of the measurement devices, spectrometers, because spectrometers always measure ratios. You have cups. You get that many O18 and that many O16. So you always have a ratio. And these spectrometers, I worked on one myself for a couple of years. They are extremely unstable. They have moods. One day you start working with them and they are shifted. There is, I don't know what happens, this big magnet doesn't work the same way. And this is why working with ratios, you overcome these shifts in the operation of the device. It makes your life easier. This was the second reason why it was done. Okay. What you probably have seen already in many papers is the delta notation. Delta is the ratio minus the ratio of the standard divided by the standard. And this is the deviation from the basic ratio of isotope abundances. And as a standard, we usually use ocean water. This is why the standard is called VSMOF, Vienna Standard Mean Ocean Water. So Vienna, the International Atomic Energy Agency, actually produces standards and sells them to laboratories worldwide that define the reference abundance of seawater and some other standards of water, and that can be used as our standard. So you have VSMOF, this is the standard mean ocean water or abundance R of ocean water, and they actually put a lot of work and technology into producing this reliably, always in the same manner. You buy small ampoules, I don't know, 200, 400 milliliters, and it costs a couple of €100, and you only get them every 2 years to use them as a standard. You also get them for Arctic water, So if you want to measure Arctic water samples, and you can also get them for carbon isotopes. So this was certain belemnite was used as a standard, and you get them for all other kinds of substances. So this is what we all know. And when this value is negative, this means that our sample has less heavy isotopes compared to seawater. Now, how many do we have? This is quite interesting. We have about 2005 heavy isotopes per million water molecules. So if you want more or less 2 per mil are heavy. I think this is, when I saw this for the first time, I was quite surprised that it's that high. Yeah? And for hydrogen, it's less. You have 155 per million, but the precision is interesting. It's plus minus 0.05, so we can actually measure the abundance of these values quite precisely. So this is what we basically do. Now, I've already mentioned the chemist's nightmare. This was like beginning of the 20th century when chemists discovered that water doesn't always have the same weight they expected of more or less 16 grams per mole. Then the first device, it was actually, the prototype was developed end of the 20s, and it was operating like in the 40s, late 30s, beginning of the 40s, near spectrometer. There were other events that have actually favored the development of environmental isotope applications. And this was the phase after the Second World War, when the United States and Soviet Union actually had the crazy idea of doing atomic bomb tests in the atmosphere, in the open atmosphere, not underground, but they had open explosions, and they actually polluted the entire atmosphere with tritium. And the idea that all these bomb tests that happened in the 50s, 60s could have an environmental impact came in the beginning of the 60s. So some scientists said, oh, maybe this is not good. Maybe we actually have a global impact. And they started measuring the impact of atomic bomb tests on the isotopic composition of the water cycle. And the activity started in 1963. It was observed that it had a massive impact on the water cycle. We have actually polluted the water cycle with tritium. By the peak concentrations in Canada and in the northern atmosphere were about 1,000 times higher than normal, all over the northern hemisphere. On the southern hemisphere, the tritium concentration was about 100 times higher than normal. And it took until 5-10 years ago until the impact of atomic bomb tests faded out by natural decay. So our whole Earth was polluted with radiogenic, anthropogenic tritium from bomb tests from the 1950s until the 2010s. Now we are more or less back to normal. There are some pockets where water is still old. We have still elevated concentrations, and in the other parts of the world. So I just listed these important moments. So this was another important moment because a nice side effect of this not so nice discovery was that we know a lot about the distribution of isotopes worldwide, and we can produce so-called isoscapes, landscapes of isotope signatures in water. And at the moment, you can download them from the International Atomic Energy Agency. Everybody can do this. You just need to register, and you can have access to the isotope data that the IAEA has collected since the 1960s. So does anyone have already access to the IAEA? Does somebody use this? So if you want to work with stable isotopes, just go ahead and go to the internet. IAEA, go to GNIP, Global Network of Isotopes and Precipitation. Now it's called WISER, it's a new database. It will take a day or so until you get access, and then you can log in and download isotope data from any point that you want in the world and in the Mediterranean. Data are sparse sometimes, so some people measured in the 70s, 80s, and then they stopped. But altogether, there is quite a nice package of data. And since 10 years or so, there's more and more activity to calculate isoscapes. There are more teams producing interactive maps. There is a climate model that integrates isotopes of water, so you can actually get calculations of isotopic compositions for different months and years for several countries. You can actually look at animations of the isotopic composition. So there's quite a lot of information available. Now, I told you that the chemists noticed that there are differences, and I just want to show them. So seawater has in our notation delta a value of 0. This is quite obvious because we compare seawater to seawater. There's no deviation. It's the same. So this is why our delta value is 0. And you see in these bars how the isotopic composition of water can actually change. The value on the x-axis, minus 50 means that you have 50 per mil less abundance. So your R of the sample has a deviation of 50 per mil compared to seawater. Yeah, so this means in total 50 per mil deviation. Can actually convert this to how many more heavy isotopes you've got per million. Yeah. So this is so 1 per mil is 2. 50 per mil means you have 100 more heavy isotopes in your sample. So you have 2,105 more or less. So then you have 1,905. This would be the composition of an Arctic water. And we can measure this deviation. Soil water is depleted. So you see the black bars are on the negative side. Groundwater is more depleted. The Rhine water as a reference is even more depleted because it comes from the Alps. We'll discuss the isotope effects in a minute. And then geothermal water, magmatic water, metamorphic water, they can be heavier. So we already have the first little tool. It's still qualitative. So seawater intrusion is the encroachment of seawater into a coastal aquifer. But it could also be caused by geothermal water, by water that is a residue of magmatic cooling. Of course, there can also be some other water-rock interactions that cause salinization. For example, serpentinization. And if the process is internal, it comes from the inside, then we often have heavier waters. Geothermal water can also be negative because of biological activity. But most of the water, most of the fresh water, the black one, has a negative isotopic composition, like -10, -8, -6, and seawater is 0. So a very easy way, besides salinity, of course, is to look at the isotopic composition and see whether we have a shift towards seawater. That goes along with increased salinity. So this is already a qualitative tool that we can use, and that is used in many, many applications. Just to demonstrate how isoscapes look like, this is the result of a study that I did with a student of mine. We took the 32 stations of isotopic measurements that we had in Germany that you can download from the International Atomic Energy Agency. Michael Stölzle produced this, and we actually created a geostatistical model that predicted the isotopic composition in Germany at every month, at every location in Germany for 1 by 1 kilometer squares. So within the METSAL project, we have worked on isoscapes for the Mediterranean, and this is what you can use as a reference. So we can actually calculate what the composition of water is expected to be at any time, at any place. And this is excellent because then we can actually, we have the expected isotopic composition that corresponds to the rainfall and recharge that we have in that place. We can see, is there a deviation from that expected value? Yeah? And if there is a deviation towards zero, it's very likely that this is an influence of seawater. So you see, if we look at the map, that on the color scale gives you the reddish means it's more towards zero, and bluish means it's more depleted, has less heavy isotopes. So we see that in the Alps we have bluish colors, high locations. When we come closer to the coast, it's more reddish. So we are closer towards seawater. The rainwater is more similar to seawater. We will see why in a minute. You see the mountain ranges are more shifted towards green and blue, so they are lighter. And we see basically all the tools that isotope hydrologists use for interpretation in one map. And these tools are. And I will explain in a minute why this is the case. We just start with the phenomenon. The higher rainfall falls, the more depleted it is. We call this altitude effect. The more distant from the coast we are, the more depleted the water is. We call this continental effect. The cooler the month is during the year, the more depleted the values are. We call this seasonal effect. So we see that there is a seasonal movement, less heavy isotopes during winter, more heavy isotopes during summer. We call this seasonal effect. This is an important feature of the water cycle that is extremely useful, as you will see later. Seasonal effect. We have a sinusoidal curve with lowest values during winter. Then mountains have precipitation in mountain areas has less heavy isotopes. We will see this later in an example from Mersin, from Turkey, where we can actually, we will also see this when we look at the study sites of the METSA project. See the different study regions, we actually see differences. So elevated areas have a lower isotopic composition, and this is extremely useful because we can detect mountain recharge. So groundwater that was created in higher mountains is detectable and can be very clearly separated from groundwater that has been created in lowlands, and definitely is very different also from seawater. And then we have a continental effect that you also see quite nicely here. So the further we are from the ocean, so this is just for those who don't know Germany that well, we have the Atlantic here. This is now Netherlands here, and we have the Baltic Sea here. So basically the weather comes from the west, and we see that depletion towards the east. And if we go to Poland, Russia, Ukraine, Belarus, China, it's getting, Mongolia, it's getting more and more depleted. Then, of course, from China, from the other side, we have a vapor transport, the same thing happening from there. So these are basically the things, and the seasonal effect is shown here. I have just picked two locations, one close to the coast and one a bit further away. You see that the coastal area has smaller seasonal variations, closer to zero, closer to the vapor source, and the continental one has a stronger, more pronounced seasonal variation, and is shifted towards more negative values. Seasonal variation, altitude variation, continental variation. So now we can make a cut here. First of all, before I go further, is the speed of the lecture okay? Do you follow well? Yeah? Is the level of complexity okay? Not too easy? Not too complicated? bit too easy. I will push harder. Okay. Yeah?
Can you please briefly repeat about the altitude variations?
Yes.
From what is it dependent?
Yes. So I wanted to make a cut here because I wanted to first present a phenomenon. And now I will explain why this is the case. Okay? So now I want to explain why we have this. So, Carlos, what about the coffee break? Not that I need it. Okay, you just want to. Okay, so I want now to explain why we have these differences. And I want to empower you, hopefully, to do the calculations yourself and to show you that everything that we observe can actually be calculated and inversely used to learn something. We can use isotopes as a thermometer. We can use isotopes as a hygrometer. We can use isotopes as a clock, as a timer. But we need to know we need to do some calculations, and I need to explain how they work. Yeah? And I will say, I will just start doing this so that you get a taste, and then we'll have a break. Yeah? So I think looking at the overall time scale, it's like 10:30, okay for you? With the break, does this work also with the organization? Okay. So then we have about 20 minutes to get into this, and then we'll have a break. So you remember well the R, which is the isotope ratio. Now we define the change of the ratio. And this is dr by R. Now, everyone who does some mathematics is already excited because the change of something above the thing that changes can be integrated. This always gives its logarithm. So this is already, we keep this in mind, this is useful. So going back to the definition, we have the change of the numbers of heavy isotopes. And we now do this for, this is one isotope, this is the other one. So we do this, we actually just use the definition that we had, R. So we have the change of the heavy isotope and the change of the light isotope divided by the number of heavy isotopes and divided by the number of all the isotopes. And this change of the isotopic abundance is called alpha. Alpha, and this is what we call fractionation. Fractionation is actually the change of isotope ratios. And we write it, the notation is like this, alpha of a reaction that goes from A to B. So this can be water, vapor. This can be water and a phase transition from water to vapor. And then you call water A and vapor B. This can also be a chemical reaction. This can be a carbonate that precipitates from water. And then A is the water that has dissolved hydrogen and carbon, and B is the calcite that has formed precipitating out of the water. Now, in many cases, A has an isotope ratio. Water has a ratio of heavy isotopes to light isotopes. And when you produce vapor, and this is the key, the abundance of isotopes will not be the same. It's fractionated. So vapor has basically less heavy isotopes than water. So you have dr compared to R. You have a change in the isotopic composition between water and vapor. Now, some science history. The funny thing was that theory came before experiments. So in the 1940s, people were able to calculate already the fractionation before it was measured. The first measurement of fractionation was done of water was done at the end of 60s, beginning of 70s, Majube, 1972, 1973, but the calculation of the fractionation factor was already done in 1948. It had to do with atomic bombs, because this was actually where all the money went to do atomic bomb test, and they were the best physicists. They did all the calculations to understand what was going on, and they developed all the theory, and then the measurement came much later on. So why do I mention this? The alpha can be calculated theoretically, and it was measured by Majouba. And Majouba found that the fractionation factor, you can ignore this for the time being, this is just a convenience. The fractionation factor depends only on temperature. This is very practical, but it depends on the reaction. So every reaction has a temperature dependency of the fractionation. And I had prepared, I hope this will work without big trouble, a very nice web page on which you can find all these. I know that I have to change the... No, you see it. This is nice. You see it also online. There is a web page that I like very much. It's called Alpha Delta. It's French, Calculateur du fractionnement des isotopes stables of the stable isotope fractionation calculator, was prepared in Canada. Yes?
I think the people in the teams, they cannot see the website. The camera and you can turn it that way.
Okay. Yes. So we have a break.
No, it's not on. There's a problem of doesn't follow.
It doesn't follow. I will solve this. This is not a big deal, I think.
I think you have to
Stop sharing. And I share.
share the entire screen.
I can do this too.
What is okay. If you share the desktop, I think, or the whole screen will be.
Yes. We'll see what happens.
Yeah. Works. But let's minimize this one.
Yes. So now you should be able to see the web page, and it's called Alpha Delta. It's a university in Canada, and this web page is a collection of all the fractionation factors. I have already calculated an example here where you choose a reaction which is water liquid to water gas, A to B. You choose the temperature, and it will calculate 1000 ln alpha. You remember, this was the left side of the equation when you had DEF coefficients for different temperature dependencies. So actually, it just goes back to the database. It picks the equation, picks the coefficients DEF, picks the temperature, and solves it. Now, you can calculate the fractionation factor, and this means this is a big progress in terms of quantitative isotope hydrology. You can predict how the isotopic composition of vapor will be at a certain temperature when water evaporates. You can predict from the composition of the water what the composition of vapor will be. Yeah? And for doing this, you just need, I hope that I come back to my presentation, I think it works. You just need to solve this equation. This equation needs temperature in Kelvin. Kelvin, yes. 2 times is 1 million divided by temperature squared, 1000 divided by temperature. And then you have these empirical coefficients D, E, F that are listed here in the table. One's for O18 and one's for deuterium. They are different. And now you just plug in these D, E, F's into this equation, and you calculate the alpha. And the alpha will tell you how much the isotope ratio of O18 to O16 changes when water evaporates at a certain temperature. And this is the very long answer to your question. Because now you will see how we will be able to convert this to isotope effects of the seasonal fluctuation and of the altitude fractionation. You already see where it's going. When we are in the high mountains, we have a lower temperature. So in the clouds where the precipitation happens, we have a lower temperature. Because of that, we get a different fractionation factor at lower temperature. And this causes a different isotopic composition of the rainfall because the temperature changes. Yes? That's a question.
Temperature is an average of the temperature of the year.
No, this is actually the temperature at the moment when the phase transition happens.
Specific.
In the cloud. Yes. So at the moment when it rains in the cloud. We know now that before it was very difficult to measure high intensity changes, but we know now they are not a technical problem.
No, but I'm just turning it on well to the board so that remotely connected people can see what you're showing.
Yes, I try to be aware of this too, so
No worries.
I will use my mouse instead to improve this image.
Okay.
Yeah?
But now it's okay.
Okay. So the question was, yes, we can measure now high intensity with laser spectrometry. We can see what happens during the rainfall. And this shows that there's a lot of variability. And we see a lot of small effects of when something happens in the cloud, it's very high, you get ice. You can see all these things in rainfall. But the simpler picture is, in rainfall, we have lower temperature. At lower temperature, we get a different fractionation. And as a result of this, we have a different value during winter and at higher elevation. Now, I need to say something that's very important. The first thing that I explain here is so-called equilibrium fractionation. Equilibrium fractionation means that we are in a more or less closed system. So let's take this one. This is a closed system. Yeah, so it's not a closed system yet. I will make it a closed system by drinking. So we have a bottle, and this bottle contains water of a certain isotopic composition. I can read where it comes from. So it's Italy. So I don't know, it's probably -4 delta. You know how to convert the delta into an R with the equation that I showed you. So what you do is you take the R of standard mean ocean water, R minus R standard divided by R standard. You have the D and you solve for the R in the equation. I'll just show you. So converting D to R is important. We will need this. So we have this. This is a value that we see everywhere in papers when we measure. But sometimes we need this one. This is the real ratio. So we know this one. I gave it to you, 2005. And we actually solve for our sample. So we can convert our delta value, which is a deviation from standard, to the real ratio of heavy to light isotopes. Okay? Now, I calculate my R, and now what happens, and we learn that this happens quite quickly, we have air above. If I want to be a bit scientific, I could actually take nitrogen and replace the air above just with new nitrogen to rinse it. And what we'll see is that water will evaporate here. So you get vapor, and the vapor will actually equilibrate with the water. Before we said it takes 24 hours, but now we know it just takes an hour or so. It's very fast. So basically there will be evaporation from the water into the vapor all the time. And the reverse process, condensation, and this happens thousands of times a second, goes forth and back all the time. And the number of stable isotopes in the water and the number of stable isotopes in the atmosphere above the water will be different. Because the heavy isotopes have a hard time leaving the water. They need to actually get out of the water. They have to overcome the surface tension. They are heavier, They have a little overweight, and because of that, their movement is slower, and less heavy isotopes manage to get here. As a result of this, you have a change in the isotopic composition in the atmosphere compared to the water. And this is predictable. It's called isotope equilibration, and the formula for calculating the isotope equilibration is given here. With this formula, you can calculate the alpha, which is the change in the isotopic ratio that happens in this bottle at a certain temperature. You got this? This is really important. This is the first step. And this can be calculated. And it can be calculated not only for water evaporation, it can be calculated for more than 800 different reactions that are all listed on the Alpha Delta webpage. So you can do this for calcite precipitation, for phosphates, for anything that you want, boron, strontium. And isotope equilibration always works the same way. You have a reaction A to B, you have a ratio before, a ratio of the isotopes afterwards, and the alpha can be described by an equation that depends on three empirical factors, in which you can actually express the temperature dependency for alpha. Once you have the alpha, you can use the alpha. I told you to ignore this for the time being, because you can just actually bring this to the other side. Once you have the alpha, you can actually calculate the new RB. Start with the value. You can calculate the new isotopic ratio after the reaction. And you already know how to convert R's to delta. You plug this into your delta function, and you can calculate your delta. Isn't this nice? Now you can start walking, yeah, doing things yourself. Yeah.
Next question. The first value of that, how can get it?
Measure. Measure. If it's seawater, it's 0. If it's inland, you take a sample, you measure. So you start with this. So this is basically a measure. You could also calculate it yourself if the delta, the starting, is a result of another reaction. But you always need to start somewhere, because you only look at changes compared to something that exists. Yeah, so you have to start from somewhere. So if we look at the global perspective, everything starts with evaporation of water over the ocean. The ocean is 0, but now we are able to calculate the composition of vapor that comes from the ocean. Now, when this, now it starts getting interesting, because now the vapor comes to Salento, and we have rainfall, which is quite rare. And now in the cloud, there will be a new temperature, and the same thing will happen, but reverse. Instead of water to vapor, we have vapor to water. So we have a reaction B to A. And the alpha is actually exactly the inverse. I mean, it's the same value, but you get it from RB divided by alpha. Now, but the precipitation happens at a different temperature. Cloud might be warmer. Because of that, the alpha will be different. That you can calculate now the composition of your precipitation that you have in Salento from the ocean composition. Start with 0, you calculate the R, get a new composition. I will do this with real values to give you some real perspective. Then the cloud is brought here. Let's assume it doesn't rain before. We have now the same reaction reversed. The vapor becomes droplet. Droplets have more heavy isotopes because the heavy isotopes condensate earlier. So the ratio will change. This time the rainfall gets heavier, but at a different temperature. And by doing this, you can actually predict the isotopic composition of rainfall at a certain location. Was this your question answered? Okay. Now let's do this really for some values, and before I do that, I will give you a perspective. I told you to ignore the 1000 ln alpha, but now we will use it. This notation was used by physicists because 1000 ln alpha is very close to delta. So this was a trick to actually get very quickly a first impression of what the delta value will be. Yeah. So this was a smart mathematical trick to give you actually already the result. You can use this one, but I prefer to do it precisely. So because you program this, you don't have to use more or less things. So you can actually use calculating alpha precisely, go to this equation, calculate your B, go to the delta definition and calculate your delta. But you already get the first glimpse of what the result will be from this one. So we will go back to the web page, and now you will see better. So I have chosen, I will go back, I hope my internet connection works, so that this doesn't become a disaster. It didn't. Thanks. So this is the page. You first give your temperature. So let's assume we have evaporation at 20 degrees. Now you choose your reaction, and you see how many you've got. You have Eckmite, studied by Singh, many minerals, illite, Pechblende, all equilibrium reactions. We try to find water, H2O. H2O was studied by Utinga, Craig, Majube, Friedman, Neal, very many. The most famous one is Majube. You click on this equation. Now, Majube did experiments in the lab to determine DEF, and he published this. And now we calculate the 1000 ln alpha of water that evaporates at 20 degrees, and we get 1000 ln alpha of 9.7. So this means that the isotopic composition of vapor is 9.7 per mil depleted compared to the water. Yeah. So this is how it works. And they also give the diagram. So here you see the temperature dependency. Now, when we do this the other way around, we will solve this again for precipitation. So could I bring this across to you? You understand the principle? Maybe also feedback from the chat. It's okay? Okay, so now let's just make a little summary before the break. We have defined the R, we have defined the delta. You know how they are connected. This is something new, but this is very simple. Whenever we don't know whether this is really a process, then we use just a Greek delta to say there is a difference. We don't know whether this is just a difference, coincidence, or whether there is a process. So we don't know whether this is reaction, so this is just to say we don't know. But if we know that this is a process, there is a reaction like water evaporating, water precipitating, calcite precipitating. We use alpha. And the alpha means that there is a change in isotopic ratio. This is just a rewriting the definitions, nothing else. And this is the resulting change in the isotopic composition. We call this epsilon. This is just nomenclatura. Yeah? But it's good to keep it and to make your life easier. And the change is also alpha minus 1 times 1000. And since alpha minus 1 happens to be ln alpha, this is the mathematical trick that was used. So we can always calculate the change of in a reaction by taking the fractionation factor minus 1 times 1000. Yeah. Once we have calculated alpha, we can actually say minus 1 times 1000. Now let's, yeah, this is equilibrium fractionation, and this is just to show you the result for the isotope effect of evaporation at different temperatures for water and ice. Ice fractionates even more because the water needs to get out of the ice structure and then into vapor. So there's more, it's a higher step. We have this for oxygen and deuterium. This looks very similar. We will look at the differences in a minute. But there's one thing that I want you to take away into the coffee break. Fractionation is more efficient when it's cold. When you boil water, the energy levels of heavy and light isotopes are not significant. They are not really important anymore. There's so much energy in the system, even the heavy isotopes get into vapor. How would I explain this? Maybe I don't want to use a bad example. Maybe doping. Doping is high temperature. So you have athletes who have a bit overweight and normal athletes who are completely trained, no overweight. And you dope both. And then the time difference for them running 100 meters will probably become smaller when they have external energy added. So it's the same for water. When you have more external energy, fractionation is weaker. But when you have less external energy, the small differences in weight become more significant. And this is important. This is also an answer to your question. In winter, fractionation is stronger. So in winter, we get more fractionation because the temperature function of fractionation tells us we get higher fractionations at low temperatures. When the ocean is cold and we evaporate at 4 degrees above the ocean, the fractionation is much stronger. So the difference between abundances on ocean water and vapor is higher. If we have a very warm ocean, fractionation is weaker. This axis, this is the temperature, and this is the fractionation. The higher the values are, the more you fractionate. We are ready. So the more you fractionate, and this is important to notice, and this is an answer to your question, why do we have seasonal variation? Mainly because the evaporation over the ocean fractionates more during winter. And this is why our rainfall is lighter during cold seasons. In summer, we have less fractionation, and this is why the rainfall is heavier. Same for high clouds, it's cool, and the fractionation happens at lower temperatures and it's more efficient. Yeah? Okay, so I think this is a good point to stop. We can elaborate and repeat a little bit on this, and then I will destroy the illusion that we understood everything, because this is now where we were in 1965 when Craig discovered that this should be the solution, but it was not, and it was a big puzzle to everyone, but it led us to new discoveries after the coffee break.